So, as usual, let's start with a quick review of what we talked about past couple of days for context, and then what we're about to do. So, before, what did we go over? We talked about logical operators, equivalences, quantifiers. So, basically a lot of ways of building and working with propositions. So today, we are going to start working in the direction of making arguments and making proofs. So we are going to talk about rules of inference, which is the basis for mathematical arguments. So let's get started. To start, some terminology. A proposition that is always true handwriting is deteriorating. Proposition that is always true is called a tautology. So when is a proposition always true? Let's look at some examples. P or not P. Here's a proposition, and it's always going to be true because if P is true, then it works, and if P is false, then not P is true. So I'm even going to write down a little truth table here, just to be super explicit. So if P is true or false, then not P is false or true, respectively. And then, so of course, or means that one of these two things has to be true. In this case, it works, and in this case, it also works. So if you look down this column, this proposition is always true. This is the kind of thing we're talking about. So this is a tautology. Let's look at a slightly, maybe I'll do that up there. Let's look at a slightly more complicated one. So another example. So P implies Q, and P implies Q. This is a little bit longer, so let's write down the truth table again, just to be explicit about it. Take some space. So we have P, Q, and then I'm going to build it up piece by piece, like we did before, so that we can tell what's going on. So P implies Q. And then let's take the next piece. P implies Q and P. And then finally, P implies Q and P implies Q. Okay, big old truth table. True, true, false, false. True, false, true, false. Okay. So this is our setup for our truth table. Hopefully at this point, this is getting familiar. So let's remember what implies means, because this is one of the ones that can be confusing. Basically, it means that if P is true, then Q is also true. So it's an if-then thing. In particular, if P is false, then there's nothing to say, and it's vacuously true. So the only time it fails is if the first thing is true and the second thing is false. This is the only time it fails, right? And then let's quickly run through the rest. So we're taking this column and this column to make this. So when are these both true? They're both true here. And never again. Okay, so the rest, it's false, false, false. Okay, and now for this last thing, we're looking at this column and this column. When does this column imply this column? So it's only going to fail when the thing at the start is true and the thing at the end is false. And this never happens, we can see, right? Because this is true, this is also true, and the rest of the time this is false. So let me erase all those notes, and then this is just true all the time. So again, this proposition is always true. This is a tautology. So what is the significance of this? I'm going to come back to it in a minute, but the idea is basically that if you want to make arguments that are true, then they need to be based in logic that is always true. That's essentially the idea. That's why tautologies are important. Oops. Geez, let me pull up the chat so I can be looking at questions. So next, let's define what is an argument. So we're going to be using this, we use the word argument in a pretty informal sense, and we're going to continue doing that. But if we want to talk about it in a formal sense, this is always what we will basically be meaning. An argument is a sequence of propositions which we call premises, and a proposition at the end called the conclusion. So it might look something like this. We have proposition, 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 therefore conclusion. So just to write it out, these are our premises. This is our conclusion. And this guy means therefore. Just a little piece of notation that is useful in these situations. And this is supposed to represent an argument where, we are taking these propositions to be true, and we're saying it follows that this proposition is also true. And then we say an argument is valid if the premises imply the conclusion. But let's be even more explicit about what that means. That means the proposition P1 and P2. So all of our premises connected by and implies Q. So this is some proposition. And the argument is valid if this proposition is a tautology, if it is always true. So this is what I meant by that comment. A valid argument is an argument that relies on logic that is always true, right? So the second example of a tautology that we gave above was this. What was it? So it was P implies Q and P implies Q. So we saw this is a tautology. We can sort of reform that into a valid form of argument. So our premises are P, and P implies Q, and our conclusion is Q. And let's just take a quick look at how we were saying that these should correspond. Our premises become this part of the proposition, where we just AND all of them together. Take all of them and connect them by AND. And then the conclusion is this part of the proposition, where it is implied by the premises. So this is a valid form of argument, in the sense that if you take any two propositions P and Q, if these propositions are true, then this proposition will also be true. In other words, these propositions imply this proposition. So let's give a very basic example of how you might actually say something like this as a concrete argument. So say we want to show that the square root of 50 is greater than 7. And we know that if some number is greater than some other number, then the square root of that number is greater than the square root of that other number. In fact, let me write this as, oops, like this, the way we were doing before. Then we can make the following argument. So we know that 50 is greater than 49. So far, so good. We also know, by this fact, that 50 greater than 49 implies root 50 greater than 7, which is the square root of 49. Therefore, we conclude that square root of 50 is greater than 7. So this is a concrete version of this argument here. And if you read the book, you may see terms like this is what they call an argument, and this is what they call an argument form. So where you're using variables like P and Q rather than actual propositions, right? So this is basically what it means to make a mathematical argument.